Just testing audio. Okay. Good morning, good afternoon, good evening. Thank you for joining us in this presentation where we will be exploring advancements in lightning strike protection. It's a pleasure to be with you today. I'm replacing my friend and good colleague, Dr. Michael Swan, who couldn't be present due to a last-minute inconvenience. So I'll do my best to go through the content and then try to answer some of your questions at the end. If I cannot answer some of them, we will get back to you shortly after. I also want to introduce Molly Johnson. Molly is our marketing and communication leader at 3M. Molly, do you want to introduce yourself? Okay, so Molly cannot go off mute. I apologize for that. So I'll go ahead and I'll introduce myself. I'm Peter Maroulis. I've been at 3M for 10 years, based in the aerospace capital of the world, Montreal in Canada. My background is in aerospace mechanical engineering, and I spent 5 years at major aircraft tiers before joining 3M in many responsibilities, including manufacturing and materials and process engineering. Within my multiple roles at 3M, I've been closely working with several aircraft and rail OEMs and focused on many different material technologies, such as liquid and paste adhesives, polysulfide sealants, surfacing and lightning strike materials, and others. Recently, I've been also prioritizing my time on our clean and hygiene program within aircraft interiors that you may be aware of. So the agenda for today will explore the question, why is lightning strike protection important for modern aircraft? Then we'll look at surfacing films with built-in lightning strike protection and how those optimized designs can provide improved processing and quality performance, in addition to possible weight reduction opportunities in comparison to legacy systems. And then finally, we'll touch on some of our exciting advancements within this field. Next slide, Molly. So starting off here, stats show that on a daily basis, there are over 8 million strikes a day that hit the Earth, which equals to about 90 to 100 strikes per second. This doesn't even include the strikes hitting from cloud to cloud. So it's a very common phenomenon. For our sake here in aviation, experts say that on average, every aircraft and commercial airline fleet is hit at least once per year by lightning. This may occur without indication to the flight crew. This doesn't lead to any accident, but the last recorded incident due to the lightning strike in the US was in 1963 when a Boeing 707 operated by Pan Am reportedly exploded due to a strike. Traditional aircraft structures have been made in metal, and there's a shift in recent years where OEMs have been making the change towards composites. The potential for damage increases with composites, thus these parts do need extra protection, and we'll touch on this in a bit. The major issues or consequences are really the loss of revenues for the airlines or operators due to aircraft on ground. There is a need to repair damages caused by the strike to make sure it is safe for it to return into the service and into the skies in an airworthy state. With that said, there are mandatory inspections that need to be done before the return into service happens. This causes delays in departures, possible flight cancellations, and other. Next slide. So knowing that aircrafts do get strikes regularly, the FAA and other certification agencies around the world have defined how to view the aircraft. We won't go into too much details here, but when you look at this image, you break it into zones where you are most likely to get the high current from the initial strike. Highlighted in orange over here, I'm not sure if you see my cursor, um, um, is zone one. Well, you'll get a lot more current, but small attachment periods. And then you move into zone two, which is highlighted in green, where the lightning will sweep across the aircraft, reattaching multiple times as the aircraft flies through the strike. You could see this in the bottom right image with multiple strike points. And then that strike leaves the aircraft, typically from the rear or trailing edges. That exit point doesn't really shift too much, and protection often provided in those areas are static strips that you would basically see sticking out from the trailing edges. So each of these zones require a different degree of protection, and these are all defined by each one of the OEMs. Dealing with a high current from an initial strike requires more protection than the lower, slower burn that occurs in zone 2 type strikes. Something to keep in mind when you're looking for different solutions and how and where they could be used on your vehicle. Zone 3 is known as the conduction zone. Essentially, it's surfaces not in zone 1 and zone 2 where any attachment is deemed unlikely. Next slide. Composite materials are chosen due to lightweight and their more flexible nature, but they don't handle current like metal. As we have alluded to earlier, metal structures tend not to be as damaged as composite surfaces. Aluminum is highly conductive, and when struck by lightning, you'll typically see paint damage at the location of the strike. And depending on the intensity of the strike, we may see some pinhole burns within the aluminum to a decent large burnout area. But again, this is not common for metal structures. Composites, on the other hand, will basically blow out if not protected. The photograph at the bottom shows an unprotected composite. You see the fibers all destroyed over there. As a result of that, there's a need to add a form of protection on that outer surface, and that's typically a conductor of some sort that will help minimize the damage to the structure. So composite parts need an extra layer of resin, which is known as a surfacing film, in order to provide a smooth surface comparable to the finish of a metal surface. Next slide. The typically technologies that are used in the industry today are shown in the slide. I have the foils at the top here. You could put a continuous foil on the structure. This comes with challenges in shop handling and conformability. We'll touch on this with these other foil technologies as we go through. The most traditional solution in the industry today is the expanded copper foil, and but we do also see some aluminum foils in uh, in this space. So expanded aluminum foils. Basically, those are materials that are cut from continuous foil by putting slots into them and then stretching the foil to create this expanded foil. We at 3M, with some of our partners, have been looking at perforated foils for the last few years. And this technique involves cutting specific pattern designs that are optimized to provide additional performance, which we'll cover in the next section. Less common, but still used a little bit in our field, are woven and interwoven conductive materials. The conductive fibers are woven in the outer layer of the fabric that goes onto the structure. Typically less effective, but maybe more efficient to put them on the aircraft during its build. And then finally, conductive coatings, which can be applied on the surface by spraying. 3M has done some experimental work in this area in the past. There are some big challenges with these coatings. For instance, ensure to get enough conductivity on those solutions, with those solutions. Another one is knowing how much material you have applied. And finally, operator consistency is critical. Could all be resolved in some ways, but definitely a challenge to be aware of. Next slide. So we really need to think about these foil solutions. And when we look at traditional expanded copper foil configurations, it's basically a network of fibers that are joined together at nodes. You need to fill that that with resin for you to get a smooth surface, which makes it important to think about it as a whole system. You see the image on the right there. You'll see it in this presentation that the combination of the resin and the conductor applied as the outer surface of the fiber, reinforced composite, which will then see a paint process overcoated. There are a lot of functions that this outer layer must perform. These are listed in the slide here. It protects the structure from damage due to lightning strike. It needs to provide a smooth paintable surface, hopefully with little to no paint holes. And there are a bunch of secondary performance requirements that make it a good system. So it needs to prevent micro cracks from forming that could allow moisture to get in, which could cause corrosion in the embedded foils. There's also a need to remove the paint and surface for various reasons. So these systems should require an adequate performance against these chemicals used for cleaning and paint stripping. They need to be conformable to contoured surfaces and repairable after damage. And finally, little to no impact on the weight. Obviously, a reduction would be nice. This is highly dependent on how much protection you would choose in each area. Slide. We've already touched on some of the content on this slide, but ultimately the surfacing resin, while a thin layer on the outer skin surface of the structure, it performs a vital function. And it's important to design a chemistry so that the cure characteristics of the resin system match those of the underlying structure. And you end up with the resin being where you want it. In the images on the right here, this is a painted piece of skin. One has a poor surface finish and the other has a good surface finish. In the left image, you could clearly see some pitting. And this is challenging and frustrating because pitting doesn't actually show up until you paint the area or after you have painted the part. So when they are preparing the skin of the aircraft for painting, it's often sanded and prepped, and any defects are filled. And so if your choice of surfacing film can provide a defect-free surface, then you could hopefully reduce a step within the paint preparation process and not be surprised by the possible telegraphing effects of these contaminants through the surface. There's also a lot of time and effort going through making sure these surfacing films have the appropriate shop handling properties. Someone can make them too sticky or not sticky at all. They need to be stored outside of the freezer for enough time. It's the first part that often goes up on a buildup and it's often the material that is left out the freezer the longest. So making sure it has a long enough out time for your needs is key. The cure profile is also key. Some films are only 250 Fahrenheit or 121 Celsius cure. Some are only 350 Fahrenheit, 177 Celsius cure, and a few, and more recently, some additional ones are dual cure at both of those temperatures. Keeping weight out of the structure is always a top priority. We've touched on the chemical resistance just before with the paint stripping process. And the in-service thermal stability due to thermal cycling seen on the exterior surface of the aircraft is also important. Next slide. In this slide, I want to expand on the differences between the expanded copper foils and the perforated copper foils. In terms of the expanded copper foils, the foil itself is cut. So there's a slit, as you could see on the image on the left, and then it's stretched. So what you end up with is those nodes that you see in between those areas, or those open areas. If you look at the cross section of the wires, when you look at the nodes, you have a large amount of copper there, which is essentially not doing much in terms of electrical performance. Theoretically, you need a constant cross section throughout the entire network. There's a lot of excess copper in these nodes. So what 3M has been working on as a design is a perforated solution that doesn't have the excess copper in those node points. If you look at the cross section at any given point in the perforated copper foil in the image on the right, it is constant throughout, and this is one of the ways we've been able to take a decent amount of weight out of our solution. Important to mention here, though, since we are not restricted with our manufacturing process, we could tailor the conductivity in any direction. So the image you see, the long hexagon facing the down direction, this is giving us more conductivity in one direction over another. If you take that hexagonal pattern and rotate it, you could then prioritize the direction of your increased conductivity. Also, if you take this hexagon and make it perfectly symmetrical, you could have X and Y conductivity matching each other. Next slide. In this slide, you will see two images of a Zone 2A strike. This is a 12-ply unidirectional composite prepreg underneath. The panel on the left has a expanded copper foil conductor with a weight of 175 grams per square meter. The dots show where the system has been grounded, and you could see the damage from the strike. On the right, the panel has a perforated copper foil conductor with a weight of 60 grams per square meter. It has a hexagonal perforation design, and you could see the damage is quite similar in size with the image on the left. So it's important to know that the results here can vary with the thickness of the paint. The higher the thickness, the more charge built up outside of the paint, which then bursts through the paint and attaches to the conductor. This results to more damage. The lower the paint thickness, the less resulting damage, hence why we chose a 355 microns thick primer and top coat system, which is usually at the higher end of what's tested. Next slide. We will see an interesting observation here by comparing an expanded copper foil film with a perforated copper foil configuration within a film. Not only can we get a better use of the metal within it, but you could ultimately use thinner foils. So as a result of that, a lot less resin is also required, which could then lead to an interesting reduction in total weight. The image at the far left, we go from a 76 microns thick copper all the way down to the other extreme at the far right here on the slide, where we have a 12 microns thick copper, which we've perforated. And if you look at the chart, you could see that the cross web and down web conductivity of a traditional expanded copper foil goes from 1.6 and 4.8. And if you compare it with the other examples that are given here, the resistance is lower, so they have equivalent or better performance in electrical conductivity. Also, if you look at the data, what we're also trying to highlight is that you could flip the orientation of the hexagonal pattern of these foils, and you could get your conductance in either direction. But in all cases, we meet and exceed the resistance that is given with the 76 microns expanded copper foil. And as a result, a lot less resin is used in here. So if you look at lines 3 to 5, from the conductor weight of 142 grams per square meter to 88 grams per square meter, and for the resin system from 150 grams per square meter to 55 grams per square meter. So some significant overall weight savings here for the potential of this type of solution. The transition from a more open resin filled area to a more streamlined system with a perforated copper foil does come with some consequence, which is that you are starting to move towards a surface that is nearing a continuous foil that we've covered earlier. Copper in particular doesn't adhere typically well to epoxy chemistries. Sorry, I'm getting a chat here. Okay. And with the limited amount of epoxy that is bleeded through here on the far right, you would need to start looking at surface treatment on the copper that you would help with the adhesion of the whole system. This is not something that hasn't been resolved, but something that needs to be considered for perforated copper foils with a much thinner configuration. Next slide. Sorry, I'm getting some chats here. Okay. Um, Here we have some examples moving from expanded copper foils to perforated copper foils. The 73 grams per square meter ECF and a 142 grams per square meter ECF are pretty standard materials in the industry. Below them, you will see the weight of the resin and the total system. Then on the right of that, the number that you see there for the PCF are what we have designed to be equivalencies to the ECF materials. And what you end up seeing here is less copper, less resin, and resulting in about a 20% reduction for the first comparison and another 26 reduction of weight for the second one. You can extrapolate this with the total weight of the system used on the aircraft you're working on, and that could be a significant number for large vehicles. So pretty exciting technology that you could really provide some solid value to your design. So one of the examples of a surfacing film that we use with these conductors is our new AF536. It is a dual cure resin system, 121 Celsius and 177 Celsius, so 250, 350 Fahrenheit, compatible with both fabric and tape systems. We have launched it and made it available with both the traditional expanded copper foils and our newly designed perforated copper foils. The material itself does have a good shop handling property, the appropriate tack, and repositionable during the application. These are great features for operators. In fact, we've incorporated a glass scrim that you see here in this material to help with the handleability, but it also controls the formability of the conductor itself, and it creates an additional barrier from sanding processes. In addition to this, we've really focused on a formulation that can help improve surface finish and minimize or possibly eliminate any imperfection you may have now in your process. It has also been tested for chemical resistance with different solvents and paint strippers. And then finally, it is available with and without a built-in lightning strike. Next slide. So the last slide here, I know I'm running a little bit over. It's a table from our technical data sheet. We offer these different configurations of materials, both in expanded copper foil and perforated copper foil, and as mentioned earlier, with the possibility of having the resin without the conductor. The arrows also show the products that you could consider as a directly replacement in terms of similarities, and you see the differences in film and conductor weight in addition to the down web and cross web electrical resistance. So just wrapping it up, since the time was short, I was not able to cover any of the other advancements, but what I could say at a high level is that there is work with these systems on AFP, so that's the automated fiber placement. So typically today, lightning strike materials are applied by hand in large sheets, and this is done on parts that are made with specialized and sophisticated equipment. So we've challenged ourselves to find ways to use the automated fiber replacement equipment with our lightning strike materials. And finally, we have started working on a novel lightning strike system, which I'm hoping we could present one day at the JEC. Thank you very much.
Thank you, Peter.
Not sure, Molly, if there's still time for questions, or do we want to perhaps take them by email?
Yes, can you hear me?
Yes.
Yes, wonderful presentation. Thank you, Peter. We do have a few minutes, maybe about 5 minutes for a few questions. I do have one in the chat from Pavan, I believe that's how you pronounce the name. So Peter, if the surfacing resin finish is smooth, how does the paint stick to it?
Smooth surface. Well, basically, this is an epoxy system, and it is compatible with the different paint systems. Normally, before a paint cycle, there's your typical surface prep that you'll do. So this surfacing film, as I pointed out before, it is compatible with clean sanding processes. So that reactivation of the surface would be, I would say, essential, either with a solvent wipe or potentially with a light abrasion.
Thank you for that. Regardless of weight, is it better to use a perforated expanded foil rather than an unperforated copper sheet for some specific reason? Can you explain a little bit?
What's the so perforated copper foil, and what's the second one? Sorry,
Oh, unperforated copper sheet.
unperforated copper sheet. So is that question with or without a resin?
They don't state. It simply says, regardless of weight, is it better to use a perforated expanded foil rather than an unperforated copper sheet?
Okay, so unperforated copper sheet, I think I mentioned it earlier in the presentation. So when you'll be applying it on the aircraft, there's always that sort of worry that it won't adhere well to your structure without the resin. So when if there's little resin, it's not going to bleed out well. It's not going to adhere well. Typically, copper, if it's not prepped properly, will have lower performance on the peel. So there are different ways. These are challenges within the industry. There are ways to do it, but the perforated copper foil here, with as it's built in with our chemistry, would provide an increased performance not only in tack on the surface, but also will provide that adequate conductivity that you would need.
Thank you. Any technology, or is there any technology at 3M available to increase the conductivity and thickness direction by modifying the resin directly?
Yeah, there is. We've been working at several items, and that's sort of part of what we're trying to achieve there with Larry Ebert's novel lightning strike system.
And then do you know of any CT scan results on the PCF lightning strike stricken panels?
So I think I'm aware of some of them. I would have to defer that to Mike and Larry, but I believe there are some.
Okay. And I believe there are some too. I worked a lot with Larry and Mike on lightning strike protection. So, and then the last question I have, it says, are there only solutions for thermoset or also for thermoplastic available?
So obviously, thermoset has been our focus since this is where the industry is pulling us towards. There is definitely some work that we're doing with thermoplastic. We've worked with consortiums in the past and currently. So what I'm saying is that there will be some systems that would be compatible with thermoplastics.
Perfect. Well, it looks like we're right at time. I just wanted to say thank you again for everyone who joined our session today. And if you have any further questions, feel free to visit us at our 3M booth at the JEC show. We're happy to answer any other questions you may have or have a chat with you. So thank you very much. Have a wonderful day.